friends. In this video, we are going to discuss about the axisymmetric elements in finite element analysis ME8692. Actually, what is meant by axisymmetric elements? The element which is symmetric about the axis, where may be a x-axis or y-axis or z-axis. That is, most of the three-dimensional problems in engineering exhibit symmetry about an axis of rotation. Such type of problem is called axisymmetric problem. This problem can be solved by using two-dimensional elements. Yes, actually, one important doubt is there. Why this axisymmetric element is going to be solved by using 2D element? Yes, actually, axisymmetric element is a three-dimensional element, 3D, three-dimensional body, but it is symmetric about an axis, so that we are only considering about any one left side or right side of the axis as a two-dimensional cross section. Then it is considered as a 2D drawing. So that 2D drawing, that 2D model is going to be divided by using elements as a 2D, two-dimensional elements, so that we are considering while solving the axisymmetric element problems by using the 2D element. And also the very best and very most important thing is, for the 2D elements, these are all more convenient for describing the cylindrical coordinates, that means r, z and theta. So what are the conditions for a problem to be axisymmetric? If a problem is said to be axisymmetric problem, means what are the basic things, what are the important things which has to be adopted or it should be followed? That means there are three important concepts there. First one is problem domain. The axisymmetric problem domain must be symmetric about the axis of revolution, that is the z-axis. And the boundary condition for the axisymmetric problem should be a symmetric about the axis of revolution, and also the loading condition. Any kind of load, where it may be any kind of load, pressure, temperature, any kind of one load, that should be symmetric about the axis of revolution. So the three important conditions that should be followed strictly, that means the problem domain, boundary condition and the loading condition, these three should be, must be symmetric about the axis of the revolution. Yeah, here the perfect example for the axisymmetric element. So what's that? A perfect example means, here, my dears, this is the three-dimensional, two-dimensional triangular element, but here it is notated in the axis of revolution z, and the another one is r, so that this triangular element is called as axisymmetric triangular element. Okay, the triangular element which is going to be which is going to be displayed, or which is going to be notated, or which is going to be represented in the r and z coordinate, means then that is called as axisymmetric triangular element. That is the basic rule. Okay, is it a triangular element only applicable for the axisymmetric element? No, certainly not. Another one element is there, four noded axisymmetric quadrilateral element. Okay, so as usual, here we are having four nodes. Okay, and each node is carrying 2 degrees of freedom, so that here we are having 8 degrees of freedom. In the previous one, in the 3 node axisymmetric triangular element, we are having 3 nodes, node 1 2 3, so that here we are having the degrees of freedom as 6. Okay, right. And here the very important another one comparison is there, my dears. So for your easy to understanding purpose, I simply excused those things. That means what is the 2D problem, what is the axisymmetric problem, how it will be notated. So basic thing is there. If ordinary 2D problem, it is going to be represented in the xy coordinate, and in the axisymmetric problem, that problem is going to be notated or represented in the or z coordinate. So that is a very very important, my dears. Okay. So here we are considering the displacement as our criteria for 2D element u of x comma y is equal to uv. There is no doubt at all. And for the axisymmetric problem, the displacement is u of r z is equal to u and w. And for stress, sigma is equal to sigma x, sigma y, and tau xy. Okay, so normal stress in x direction, normal stress in y direction, and shear stress in xy plane. So here they are saying it as. And for the axisymmetric problem, sigma r, sigma theta, sigma z, and tau r z. What is that? Radial stress and circumferential stress and longitudinal stress, and the final one is the shear stress in RZ plane. So that's the logic behind here. So in addition to this axisymmetric element, we are having another one stress is there, right? Okay. And the strain E is equal to EX EY nu XY. That means strain in X direction, strain in normal strain in Y direction, and normal shear strain in XY plane. Here ER, EZ, E theta, EZ, and nu RZ. What is that? Radial strain and circumferential strain, longitudinal strain, and the final one is the shear strain in RZ plane. And the final one is the body force. So what is that body force? F is equal to Fx Fy. So body force in x direction, body force in y direction. So here in axisymmetric element, F is equal to radial force and the longitudinal force, right? So these are the very important convention, and it's the important notations we have to kept in our mind. So that is a very 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 most important thing. Okay, my dears, right? So in this session, we are going to discuss about the derivations of axisymmetric element. As usual, whenever we are hearing the derivation FEA, it starts from shape function, right? Shape function n, and next followed with our stress strain relationship, okay, and D matrix, and the strain displacement relationship matrix B matrix, and followed with the stiffness matrix, and finally it was going to be as a force matrix. So as per the list, first we are going to discuss about the derivation of the shape function. So in this derivation of the shape function, first what we are going to do means, so this is a consider there is a three noded axisymmetric triangular element. So here we are having nodes 1 2 3. Each node is having two degrees of freedom, u1 and w1, u2 w2, u3 w3, and their respective coordinates r1 z1, r2 z2, and r3 z3. Whenever we are going to write or explaining the axisymmetric element, just we have to write those things, okay. And therefore the displacements u is equal to, so here we are having three nodes, each node is having 2 degrees of freedom, so that we are having six displacements, u1 w1, u2 w2, u3 w3. And the triangular elements has a 2 degrees of freedom, so that it has a 6 generalized coordinates. So therefore u is equal to a1 to a1 plus a2 r plus a3 z, while the meantime w is equal to a4 plus a5 r plus a6 z, right? Where a1, a2, a3, a4, a5, and a6 are the general coordinates. So as usual, here we are having u1, u2, u3, a1 plus a2 r1 plus a3 z1. Likewise, u3 is equal to a1 plus a2 r3 plus a3 z3. So now we are going to arranging these three equations in a matrix form. We will get it as u1, u2, u3 is equal to 1 r1 z1, 1 r2 z2, 1 r3 z3, which is multiplied with a1, a2, a3. Now ultimately what we are going to do, this particular a1 a2 a3 is equal to, that means we are going to having the inverse of matrix 1 r1 is at 1 r2 is at 1 r3 is at 3 into u1 u2 u3. So ultimately here we are going to find out the matrix inverse. So as usual, the same procedure which was followed in the previous chapters, which is going to be followed here. So D inverse is equal to, okay, cofactors transpose divided by modulus of D matrix. Therefore C11 C12 up to C33 was found, and finally those cofactors are cumulated or simply arranged in a determinant, and then we are going to find out the CT, that means cofactors transpose. And finally we know the D matrix, so that from that D we are going to determining the modulus of D matrix, and finally we are substituting in that equation a1 a2 a3 is equal to, we will get the value. and already we know about that the area of the triangle A is equal to, so if we are going to find out the area of the triangle by using the matrix formula, we will get the 2A is equal to terms. So this term is going to be similar into the previous case, so that A1 A2 A3 is equal to 1 by 2A into, and the remaining terms are going to be followed. And here this matrix is looks like a very large one, so that these 9 elements are going to be squeezed or the converted as a very single representation as alpha 1 alpha 2 alpha 3 beta 1 beta 2 beta 3 gamma 1 gamma 2 gamma 3, right? And here the remaining values are available. So already I mentioned it, how to write, how to keep these values or how to write these values. Alpha 1 is equal to, so alpha 1 is equal to 1 2 3 minus 3 2, right? Alpha 1 is equal to R2 is a 3 minus R3 is a 2. Alpha 2 is equal to here 2, then we have to follow 3 1 and minus 1 3. So that's a logic behind here. And this is the way we have to keep alpha 3 is equal to 3 is there, so 1 2 minus 2 1, so that's a logic. And beta 1 is equal to z minus z, so 1 2 3 z2 minus z3. So like that we will keep these values in our mind very easily. Already we know that u is equal to a1 plus a2r plus a3z, right? So from that we are making it as a matrix form. We will get it as u is equal to 1 by 2a into 1 r z into alpha 1 alpha 2, which is multiplied with u1 u2 u3. And my dears, here we are going to substituting the values. We will get it as u is equal to alpha 1 plus beta 1 r plus gamma 1 z by 2a, alpha 2 plus beta 2 r plus gamma 2 z by 2a plus alpha 3 plus beta 3 plus gamma 3 z by 2a. So here u is equal to, generalizedly we may take it as u is equal to n1 into n3 into u1 u2 u3. So what is meant by n1? N1 is equal to alpha 1 plus beta 1 r plus gamma 1 z divided by 2a. Okay, so likewise w is equal to n1 into n3 into w1 w2 w3. Okay, so u is equal to n1 into n3 into u1 u2 u3, w equal to n1 into n3 into w1 w2 w3. So the remaining thing is, what is the similar one, that is a shape function n1 into n3 is equal to, right? So this is the shape function behind this. And finally u is equal to u is equal to n1 plus n1 u1 plus n2 u3, multiplying with those things. So finally we will get it as u equal to, the coordinates are r and z, so that u of r comma z is equal to u of r comma z, w of r comma z is equal to n1 0 n2 0 n3 0 0 n1 0 n2 0 n3, which is multiplied with u1 w1 u2 w2 u3 w3. So that's the logic behind here, my dear sir. Now another one derivation, that is strain displacement matrix, that is B matrix. So following, continuing of the previous derivation, u of r comma z is equal to u of r comma z, w of r comma z equal to n1 0 n2 0 n3 0 0 n1 0 n2 0 n3, which is multiplied with the u1 w1 u2 w2 u3 w3. So we can write it as a equation form, u is equal to n1 u1 plus n2 u2 plus n2 u3, right? And here we are having, my dears, the strain components are radial strain er is equal to dou u by dou r. Okay, so that is going to be simply applied in the previous equation. So it is changed as a dou n1 by dou r plus u1 plus dou n2 by dou r plus into u2 plus, like that it is going on. So what about the circumferential strain E theta, that is E theta is equal to u by r, that's the standard equations are there. So we are adapting those equations by converting the previous equation. We will get the three equations. So these values are going to be arranged er, e theta, ez, nu rz, and we will get it as this one. Okay, and n1 already we know, n2 already we know, n3 is already we know. Then we are finding out each values, dou n1 by dou r and dou n2 by dou r, so like that it is going on. And finally we are simply applying all the values in the equation. We will get it as E is equal to B into U in terms. So where B is a strain displacement. So now it is, this term is going to be called as matrix B. That means strain displacement relationship matrix. Okay, so that was represented here. And what about the remaining values? What is in by alpha 1, what is in by alpha 2, what is in by beta 1, what is in by beta 2, what is in by gamma 3, like that it is nu 3 which is going on. Another one derivation is stress strain relationship matrix. So from the Hooke's law equation, we are getting some normal stresses, that is sigma x, sigma y, sigma z, and tau x z. Okay, so from this here, just you go through closely watch it. Here we are having x y z, but unfortunately we will have a r. What's that? Very good. R, theta, and z, isn't it? So we have to change those coordinates for our convenient one, so that substituting x is equal to r, y is equal to theta, we will get the above equation, which is going to be changed as theta. Okay, so radial stress, circumferential stress, longitudinal stress, and the shear stress in r z plane. So we will get the we got the values like this, right? And which are all be going to be consolidated as a theta r, theta z, theta sigma z, sigma r, sigma z, sigma tau r z is equal to E by 1 plus V into 1 minus 2V. So we will get the one particular formula. So from here, sigma is equal to, that is ultimately the governing equation of stress, sigma equal to D into E. So that here we are having this term is going to be represented as a matrix D, stress strain relationship matrix for axisymmetric element. So that is represented here. Okay guys, and finally we are having the stiffness matrix K. So already we know about that governing stiffness matrix equation. K is equal to volumetric integral of BTdB into dV. So that dV is going to be replaced by using 2 pi RA. So what is in by R? It is an average R1 R2 plus R3 divided by 3. Okay, and we are applying those values. Already we know about that B matrix, already we know about the D matrix, which is going to be applied here. We will get the K matrix, stiffness matrix for axisymmetric element, and the final one is temperature effect. So temperature effect Ft, that means temperature force. Okay, so Ft is equal to BTD into E, especially thermal stress, okay, thermal strain, into 2 pi RA. So that is going to be called as, for axisymmetric triangular element, Ft is equal to F1U, F1W, F2U, F2W, F3U, F3W, and strain E for temperature effect is equal to alpha delta theta 0 alpha delta theta. So thank you so much for watching this video, and so happy to meet you again. Thank you so much guys. So